All right. Hello, everyone. Welcome to Project Guardian 2.0. This is guided replanning for dynamic navigation and exploration into safety systems for autonomous architectures. This is actually a presentation slide I prepared for MAE 248, a class that I'm taking this quarter, winter of 2025. We thought that at Triton AI that this would be a good introduction slide deck for any new members of the club. So I decided to just make a video presentation going over the slides. You could have a voice just guiding you through the slides at least. And it's something to watch or something to send to people that are just getting into the club. So what this presentation actually is oh, let's skip that. This is a visual guide to the Triton AI autonomous go-kart software architecture. So we're going to go ahead and start with the system overview. Let's get right into it. Let's talk about the hardware first. So if you walk into the lab, you'll see that the go-kart is equipped with a Jetson Xavier. And I was informed that this is running Ubuntu 22.04. So if you go into the lab computers, you'll see that if you SSH into this, or if you no machine into it, it'll be running ROS2 Iron on Ubuntu 22.04. And this is the high level control. And then we have a embed OS on the low level control on the STM32H743 Nucleo 144 board. And here's a picture of it as it would appear on the cart, obviously with some more wires going in and out. And here's some pinout if you want to pause and check that out. All right, let's talk about the software. So I went ahead and studied the current GitHub repo, and this is of 2025. And currently, this is the architecture of the software stack that I studied. So we have six modules, or the software can be divided into six modules, which is control, communication, actuation, safety monitoring, perception handling, debugging utilities. This is a higher level view. So let's go ahead and look at the system divided into functional modules. So we have a controller, which manages high level state transitions and issues actuation commands. We have an RC controller, which handles manual override via a remote controller. And um, next, we move on to the communication. So manages the data exchange between controllers and external systems. We have actuation, which converts control commands into movement, so steering, throttle, and brake. We have the watchdog, which monitors components and resets the system if failures occur. We have a state machine, which ensures valid transitions. So the cart can transition from uninitialized to active to emergency mode, for instance. That's just one example. We'll talk about the state machine later on. You'll see a more detailed representation. We have sensors, which collect data from hardware components, cameras, LiDAR, IMU. The slides that I actually made this project for have to do with integrating this sensor stack. So LiDAR and cameras and how to fuse that data together and, pipe it into the system. But we'll talk about that later. I'll actually talk about the project proposal that I had. And then finally, we have tools which implement profiling and logging utilities. So let's this is the files you'll see if you go on the Triton AI GitHub, which is public. The important one to pay attention to is the source folder, if you're working in a ROS2 architecture, and all the functional modules we just talked about are actual files that you can find there, and you can look at the code yourself, study it. I highly recommend it. You know, put it into an AI, ask it to explain it to you, or just study it yourself if you know how to read architecture like that. We're going to go ahead and start with main CPP. I'm going to walk you through an explanation. So this is the main function, and it's the one script that calls other scripts and kind of ties them all together. So this is the main system entry. It's the main CPP file, and it initializes the controller class, which manages high-level control logic. This defines an interrupt-based reset button. So this is button.rise, and then this is like the name right here. So this runs an infinite loop to keep the system operational. I'm going to outline some important code along the way, but let's not get too much into the details now. If you want to look at the software and study it, I highly recommend, if any of these slides interest you particularly, go ahead and look at the script yourself and really study it. I'm just going to show you high level things and the most important, highlights of the script. And so this main CPP basically ensures the system startup, control initialization, and manual reset capabilities. So let's move forward to the actuation. So the actuation can be found in the actuation folder, and this is responsible for sending motor control commands, steering, throttle, braking. It uses a VESC motor controller over CAN bus. So if you go into the lab, you'll be able to see, or you can ask one of the Triton AI members who are more experienced to point out the VESC to you and maybe even explain if they know what CAN protocol is. At least I know in the past I used the CAN protocol to control the brake for the go-kart. And I remember doing that off an Arduino and a Shield, but now it's done off of the Embed OS platform. So this actuation folder implements set throttle command, which sends throttle commands, set steering command, which adjusts the steering, angles, set brake command, controls braking force, and calm can set speed, and calm can set angle, which sends the CAN messages. So definitely something to look into. And overall, this bridges high-level control commands to physical actuation CAN bus. Let's look at the communication now. The communication details can be found in the COM folder. The scripts can be found in the COM folder. And these scripts handle USB and UART serial communication between the STM32 and external systems. So the main functions that this implements is send, which transmits structured packets. You can look at the GKC packet. It sends or has a function recv callback or receive v callback, which reads incoming data. And we have the watchdog callback, which detects failures and resets the STM32 if need be. So this ensures reliable data exchange for control updates. We have high-level control. So we have a controller folder, and this manages the overall control logic of the go-kart. This implements these main functions here: AGX heartbeat, which sends system state updates; packet callback, which handles incoming control packets; set actuation values, which converts control commands into actuation. And overall, this links decision making to actuation, ensuring safe state transitions. Next, we have the manual override, arguably a very important module, and this can be found in the RC controller folder. And this processes joystick inputs from an RC remote. This implements the functions update, which reads RC signals and publishes control packets. Another one is get autonomy mode, which determines if the go-kart is an autonomous, manual, or override mode. And packet callback, which overrides commands if manual control is active. Overall, though, this allows seamless transition between manual and autonomous driving. Okay, so next we have the sensor management folder, and this can be found in the sensor folder. This collects data from onboard sensors and packages it into the sensor GKC packet, which this folder is particularly interesting for me because implementing a perception stack, you would need to send a sensor GKC packet. So this module implements register provider, which adds a sensor to the system. You know, maybe you have a LiDAR, maybe you have a camera, a remote provider, which removes a sensor from active use, and a sensor pull thread implication, which runs a background thread to fetch sensor data. So this allows integration of multiple sensors, and this includes perception-based inputs. Okay, let's talk a little bit about the state machine, which is a very important component of this whole architecture. And this can be found in the state machine folder. This manages the go-kart's lifecycle states. So the go-kart can be uninitialized, and it transitions to initializing. And once it's done initializing, it goes into inactive mode. You can transition it into active, so it's in operational mode. And then if anything goes wrong, it goes into emergency mode. Um, this folder implements initialize, activate, deactivate, emergency stop, reinitialize, all very fundamental functions. It implements common checks, which ensures correct transitions, and NBIC system reset, which resets the STM32 if there's a major failure in the system. This enforces valid control transitions and ensures the system safety. Very important. And we got to talk about the watchdog system, which is, you know, the guardian of the whole system, and why I named my project Project Guardian, because this is just another study of a safety system. So the watchdog can be found in the watchdog folder, and this monitors the system components and resets unresponsive modules. It implements a couple interesting functions, one of them being add to watch list, which tracks monitored components. We have the watchdog callback, which resets the STM32 if any failures occur. And we have the start watch thread, which runs in the background, checking system health. So the watchdog is continually timing pretty much every device on the system. And if it doesn't respond in the proper amount of time, it knows that a failure has occurred, and it sends that down the pipeline to do the proper shutdown operation. And overall, this ensures fault tolerance and real-time stability. And then we end with the debugging and performance monitoring. So we can find this in the tools folder, and this provides profiling and logging utilities. This just implements the profiler, which tracks execution time of key processes. We have the control, the sensor communication, and then we have a logger, which standardizes the logging system for debugging. So this overall ensures performance optimization and debugging capabilities. Okay, that was a lot of details. This is mostly what I want you guys to remember. If you're going to watch this multiple times, you can definitely go back over the past slides. It'll give you a really good conceptual representation. And then, like I said, nothing beats just studying the code itself. Go in there and, just learn what's going on. But overall, you get a conceptual representation. This is the overall system flow. So we have system initialization. Main CPP starts the controller, and the controller initializes communication, sensors, and actuation. We go into this state here, which is the code control execution loop. Um, Perception to be integrated. So what I'm working on this quarter, and possibly maybe what you're working on in the future, anyone watching this, or um, maybe it's already implemented and you're improving it or something like that. But perception processes the sensor data. The sensor reader collects sensor readings. The controller processes control packets and determines actuation values. And the actuation controller executes throttle, steering, and braking commands. So during this process, we can also have manual override handling. So this will kind of hijack this control loop right here, which if RC is active, RC controller overrides autonomous commands. And then overall, just, as we said before, watching over the whole system, we have state and safety monitoring, which is the state machine enforcing valid state transitions, and the watchdog detecting failures and resetting components if necessary. Okay, so if you don't want to study any perception, you can stop the video here. That was pretty much the architecture that you need to know to get into Triton AI, at least on the autonomous go-kart project, and just a good overview in general of how a autonomous car or autonomous vehicle system works. Next, we're going to talk about what I proposed for my safety for autonomous systems class and what I got in touch with Jack and all the guys at Triton AI, um, where I could come in and help them out. And they said that I could help out if I want to help out in a safety system, I can implement the perception. So we're going to talk about a rough blueprint of how one might implement a perception stack into here. This is an ideal situation. I only have 5 weeks to do this, so I don't know how much I'm going to get done on this, but for anyone watching this, you can pick up maybe where I left off, or if you have to restart from scratch, here's some bare bones ideas on how to do it. So let's get into it. All right, so we define the perception stacks role. So let's start with that. So what are we adding? We're going to add a real-time perception pipeline that fuses camera and LiDAR to detect obstacles and update trajectories dynamically. So currently, as of 2025, we have an OAK-D LR on the front of the car, and we have a LiveOps HAP LiDAR on the front. So my task would be to figure out how to, interface with these sensors, get the proper drivers, how to access the topics in the ROS2 framework, and then obviously how to fuse this data to make it useful to our control system. So um, I would need to focus on, let's go to the second bullet point here, which is integration with the existing control system to modify plan waypoints when an obstacle is detected. And if there's a potential emergency stop that we need, if there's a collision risk, we need to execute that. So where does this fit in the current system that Triton AI has? The sensor module, sensor reader, currently processes data from available sensors, but it doesn't include perception-based obstacle detection. The controller module, controller, receives and processes control packets, only follows predefined GPS waypoints. I believe they call it a pure pursuit controller, but I'm still learning what they currently have. But my goal is that we need to inject perception outputs into the control pipeline so the go-kart can identify obstacles in real time, modify its trajectory to avoid them, and then stop safely if no alternate trajectory is available. Um, so what are the integration plan details? That's all, it's all nice to talk about, but like, how are we actually going to do this? So some ideas are, laid out here, which our first step would be to modify sensor reader to include this camera LiDAR fusion. I've already actually interfaced with the sensors. I made these slides, I think a week ago, and I've been actually in the lab messing with the Livox HAP and messing with some of the OP depth cameras and being able to see the feeds. So um, I'm getting closer to figuring out that camera LiDAR fusion, but we're basically going to need to create a new sensor provider for perception. We'll call it perception provider, and this will subscribe to the camera and LiDAR topics in ROS2 and process the data. So we have to implement obstacle detection in real time. In the lab, we have a white box. So our first goal is we have these big, ice chest looking white boxes, and we want to detect those if it's in front of the cart. Our first goal is going to be, bring the cart to a safe stop, which would mean gradually braking, sending the proper control commands to come to a graceful, stop within a safe distance from the white box. And this might involve computing the obstacle bounding boxes in 3D space. We're going to need to package perception data into the sensor GKC packet and send it to the controller. And this will include obstacle position, size, and confidence score on if this is a proper obstacle or not. I've actually been messing too with OakD is capable of running YOLO V3 models on the camera itself before you even send it into, your main computer. So you're offloading a lot of the computing onto the camera. Super cool technology. I've never used it before, but I got it up and running the other day, and it was very impressive how fast it can run an onboard, embedded chip. Let's move on to step two now, which is we would need to modify the controller to process perception data. So we'll need to add logic in the packet callback to process the sensor GKC packet from perception. So if there's an obstacle and it's detected, we'll need to call some sort of trajectory replanning function. I know trajectory estimation is not as easy as it sounds, and it's a bit of a complicated subject, at least from what I've seen in what's currently out there at the cutting edge. But if there's no valid trajectory found, we need to trigger an emergency stop. So whatever the emergency stop that we implement first is what would need to trigger if we couldn't find a trajectory around the white box. And then we need to publish the updated trajectory as a new control GKC packet. Step three would be to implement a trajectory replanning algorithm. The input to this would be the current trajectory and the obstacle location. The output would be a modified trajectory that avoids the obstacle. So, there's currently a bunch of algorithm choices. I was told about the peer pursuit controller is the GPS waypoint following. That's what we have. So we could just make some sort of dynamic peer pursuit modifications. We could do some sort of graph-based search, depending on, how much computing power we have and maybe some sort of optimization based planning. Uh, the trajectory has to be computed in real time, and we're setting a goal of maybe 30 hertz or better would be ideal. Step four would be to integrate the emergency stop with the state machine. So we need to modify the state machine to transition to emergency if an unavoidable obstacle is detected. We'll need to possibly modify the watchdog to monitor reception data, or we will need to. And if perception stops publishing, if the car goes blind, we need to trigger a safety system, or a safety stop for the go-kart. Okay, so yeah, this is just a ideal project timeline that I came up with, or things that I would love to implement. This is 6 week timeline. This could be extended over whoever's watching this video if you just plan to try this out for yourself or learn. But in week one, I'm going to try to set up some ROS2 nodes for camera and LiDAR fusion. I've already been able to display the camera and the Livox LiDAR from some launch files, in ROS2. So we're doing well. I'm gonna have to look into the sensor reader and figure out how to make this perception provider. In week two, I'm planning on implementing the real-time obstacle detection. I've already, been messing with the YOLO V3 model, so I'm already working on things in week two. And we just have to test the white box recognition with camera and LiDAR fusion. So we'll see how much we need to actually rely on the LiDAR because the camera has a lot of depth sensing. So we'll see if we even need to fuse that kind of data. In week three, we'll modify the controller to process perception data, implement the trajectory replanning logic, maybe. Week four, to test trajectory replanning in simulation or real world condition. And week five, integrate the emergency stop logic, which I believe I'm going to focus on this first. And then we'll finalize the system performance testing. And in week six, we do final debugging for performance optimizations and project report preparation. But that's for me personally. Okay, so these are just some interesting facts. You can either exit the video at this point or just listen in if you want to learn why uh, I did this project in the first place. So what was I trying to do? We're integrating camera lidar fusion into the Triton AI go-kart perception system to enable real-time obstacle detection and trajectory replanning. So this is a bit of a summary here of the whole presentation. The system currently follows predefined GPS waypoints, but lacks dynamic obstacle avoidance. So this project will detect obstacles using vision and LiDAR data, modify the go-kart's trajectory in real time to avoid obstacles, and trigger an emergency stop if no safe path is available. So who cares? Why is this important? And this was a question proposed by my professor for our project proposals. This is applicable to the autonomous vehicles industry. The obstacle detection and avoidance are critical for self-driving technologies. We have competitive racing teams. So the F1 level autonomous racing team, they race Indy cars, not on cars, but this is the IAC Indy Autonomous Challenge. They already implemented perception-based control, and our go-kart should follow, some sort of similar approach. They use, as I looked more into it this week, they use three LiDARs, and so it's definitely different. We're gonna have to build our own sort of pipeline, but similar perception stack, at least on the higher grade Indy cars. Academic research, I'm doing this for the class because I would just love to learn. I'm super fascinated by ROS 2. This project aligns, with my grad level safety for autonomous system coursework, and it's going to serve as a valuable case study for real world perception integration, at least for Triton AI. And I just, it's good to be back in Triton AI. I did a little bit of work in undergrad for the EV Grand Prix. I mostly did wiring and like electrical schematics and just low level control. And then, I've worked my way up through my master's degree in robotics now. So I want to do a little bit of work at a higher level now and, see what that has to offer. So this is a wonderful opportunity to do that and just learn as much as I can in the next, 5 or 6 weeks. Um, so what are the tests to check for success? So these are kind of like, these four green check marks are the goals I want to hit for this project. Or if I don't hit these are things you guys should try, whoever's watching this video, um, try to go for if you signed up for Triton AI this quarter and you're on perception. So we have obstacle detection accuracy. So can the system reliably detect white boxes in real time? And we need to test, once we have this up and running in consistent lighting, we need to test it with varying lighting and sensor noise and improve the robustness of our obstacle detection model. And then we have trajectory replanning performance. Like I said, trajectory replanning is a bit of a more complex subject, but this would be, does the go-kart successfully replan its path when an obstacle is detected? We would need to compare modified trajectories versus predefined GPS waypoints, the pure pursuit controller, as it was described to me. We have the emergency stop execution, which I believe is going to be the main focus for me the next 5 weeks. I believe that's a more manageable project. And this is going to be, if an obstacle is unavoidable, does the system immediately halt? We need to test the reaction times and fail-safe reliability. I've had discussions with Dr. Herbert of the Safety for Autonomous Systems Lab located in Franklin Hall, and she was saying that I can maybe look into control barrier functions or just determine some sort of gradient to safely bring the cart to a stop if it detects that white box, like I said before, in a graceful manner. And then lastly, we have the system stability and latency. So just, standard, does the perception pipeline maintain low latency processing, less than 30 milliseconds? And does it ensure no major delays in trajectory execution, which, operating at high speeds, we need to be replanning that trajectory very, very quickly because, it's no easy path to do that. So um, I just want to say thank you for tuning in, and I'm super happy to make this video, and I hope this helps somebody in the future and gives you a quick overview. You watch this, and then, within a day, you're already caught up with most of the architecture. You go in, you look at the card again, and you see it differently. And then I hope this you piggyback off of this and just continue learning. Keep studying ROS 2 and or whatever subsystem you're working on the car. I hope this helped you out to just at least get familiar with everything that's going on. So with that, I'm going to be uploading a couple videos for uh, the next 5 weeks just to document some things, and I'll leave them on my channel for however long. So hopefully this helps out whoever needs it in the future. With that, this is Dallas Dominguez signing off. And I hope this helped you out and you learned a lot. See you next time.